And here is an example of something going on for a few hours. What we're looking at is the limb of the sun. The sun's actually underneath that horizontal line. And what's highlighted here is in the light of H alpha. This is the N equals 2 to 3 transition in hydrogen, for those of you who know physics and stuff. And hydrogen being the most abundant element in the universe, of course, is very abundant in the sun. And so the light in this particular transition shows us all kinds of weird and wonderful things. At the bottom, you see kind of a grass blowing rapidly in the wind. This is stuff extending into the solar corona. So the surface of the sun is actually that curved surface there. There is something called the chromosphere hidden under here, and this is the very top. And these little jet-like things stick up. But what I draw your attention to is this is supposed to be a low beta plasma. If you remember what Fausto was saying, the energy density in the plasma in the high layers of the sun, because of the gravitational stratification, it drops off very rapidly through these layers of the atmosphere here to produce a very tenuous plasma here. This is all supposed to be in a low beta state, where we would expect to see fairly laminar looking flows. Well, here I think you can see evidence of eddies and turbulence. Indeed, if we're seeing a magnetic field attached to this plasma, which we must be, then that magnetic field must have some pretty interesting turbulent components to it, even in a place where the magnetic stresses are supposed to really dominate. So I quote from The Three Witches. The Three Witches are these characters in the play which visit Macbeth and make these predictions for him and one of his colleagues. And the predictions are that there's going to be some serious consequences for the characters in this play. And they quote, "Double, double, toil and trouble, fire burn and cauldron bubble." This is a very famous thing in English language. You hear this on the TV and adverts on the television sometimes. The sun this is a nice, I think, metaphor for the sun itself. There is a lot of toil and trouble in the sun. And there's burning, bubbling. This is what drives what's going on. A button where? You want me to click on one of these? This is extremely frustrating. What's hard to do is that I can't see what I'm doing here. So what would you like me to do? Great. Oh, God. Does somebody know how to fix this? Let me unplug it. Yeah. You can. Excelente. Muchas gracias. Okay. All right. So I just want to point out that what I'm going to do, because I'm not going to offer up in the last few lectures, I'm going to talk about specific problems with things like dynamos and physical issues that the sun shows us. There are some fundamental problems concerning the concepts of things like turbulent diffusivities that we just heard about and their role on the sun. So what I'm going to do instead is point you to what I think are some important things here. One is the essential. So these are actually articles. So the important ones, I think, containing the essence of how we go about knowing that, measuring quantitatively the magnetic field on the sun. This is the best article I've found. It may look a little scary for those of you that don't like quantum electrodynamics, and I don't, but it's really not that scary. It's beautifully written by a colleague of mine, Roberto Cassini. Matthias Rempel recently gave some lectures on the creation and destruction of magnetic fields and has written this up as part of an educational program elsewhere. I saw no reason to repeat any of that. So these are on this website right now, and during the week, I would suggest at least looking over these things because they will help you understand what's going on, give you perspective. The bulk of what I will talk about later will be some of the criticisms of the standard picture of creation and destruction of magnetic fields. Two important characters of which are Henk Sprout and Gene Parker, both Hale Prize winners in solar physics. Indeed, this is a critical review of how the sun works. And then Parker takes another look with his a beautiful title, A State of Our Knowledge and Ignorance. I think that's a very provocative title. This paper is almost steadfastly ignored by anybody working in dynamo theory. Basically, I believe that's because it's the inconvenient truth, if you know where that phrase comes from. Okay. So what is the sun? Let's get done by 1:30. So if I were the sun and writing an autobiography, I'd write something like this. I was born about 5 billion years ago from the debris of my exploded, overweight parents. And while quickly plumping into a fast-spinning spheroid because I did not have zero net angular momentum, it's very hard to have stellar clouds form without some angular momentum being accompanied by that accretion process. And I formed a large spheroidal thing with a disk around it of material. We know that angular momentum causes this kind of structure in stellar formation. The disk later shriveled into 8 or 9 small children, depending on who you ask. When I was a boy, it was 9. When you, well, maybe were children, some of you, it was reduced to 8. I started eating myself from the inside, and I don't seem to be able to stop, and I'm about halfway done. Now, after some initial giddiness of spinning a lot, I slowed down to spinning a fairly sedate, regal kind of, 1 turn a month. And this was something that's on the slow side compared with many stars that we observe. But it's typical for stars of my age, middle-aged star. So one of the things I can't abide is electric fields in the moving frame of the plasma. So if you remember what Fausto was saying, E plus B cross B is around 0 throughout the sun, unless we're in some very special circumstances. And this will have extremely important consequences. I want to draw your attention to just a beautiful discussion by Gene Parker Conversations on Electric and Magnetic Fields in the Cosmos. If you think you understand electromagnetism, read it, because you don't. Unless your name is Parker or begins with P. So for instance, the stretching of field lines comes with a real work against a tension force in the magnetic field. Gene talks about where the physical origin of this force in terms of mechanics, and has simple mechanical pictures in mind about how to express these kind of how to interpret these kind of things in terms of the Maxwell stresses and what have you. This is about $40 US dollars, so it's quite a lot of money for a 180-page book. But if I were to supervise any graduate student, anything to do with plasma or astrophysics, I recommend they buy one book. This would be it. It has a variety of very short chapters addressing concept of electric fields, magnetic fields, field lines, Maxwell and Poynting, moving reference frames, magnetohydrodynamics. Final chapter is singular properties of the Maxwell stress tensor. This is the argument that Parker has used over many years to say that what Fausto was talking about, in particular in a magnetized plasma, is inevitable, namely that even if you have incredibly high magnetic Reynolds numbers, the plasma is going to generate very small scales spontaneously without you having to drive it. And that's a very important statement that's presently unproven and a subject for great research and debate. But part of the reason we're here in this school is I want to introduce you to some of this debate. I was born with magnetic fields that keep giving me periodic irritating spots. One of the reasons I just brought this up then is that there are no measurable magnetic monopoles in the universe that we know of. Can anybody volunteer what would happen if we had magnetic monopoles present on the sun? Can I guess what it would look like? What would the sun look like? What would, given that if we look at the fact that electrons move very quickly to short out any electric field on the sun, if we had monopoles and they were mobile, they too would be mobile sufficiently to short out any magnetic field on the sun. Therefore, in the frame of reference of the fluid, if there were magnetic monopoles, then not only would we know no electric field because of the present universe we live in, but if our universe had magnetic monopoles in it as well, Parker argues that the sun would look purely hydrodynamic. It would look like seawater. You follow that? If you believe that the electrons short out the electric fields in the frame of reference of the moving fluid, if we had magnetic monopoles, they would also be shorted out, and we would have no magnetic field, no Lorentz force. We wouldn't even probably be here. Okay? Fascinating. That's the kind of insight that's in this book. A sideways look. The acne, I mean, the sun gets, I keep getting these irritating spots. The acne is quietened down for a century or two, actually during the reign of Louis XIV, 1645, 1710. It was very difficult to find sunspots. That wasn't because people had bad telescopes or bad eyesight. It was because they were looking hard for them and they couldn't see them. There were very few aurorae in the sky during this period as well. Newton arrived in this period. People like the Astronomer Royal of the time, I can't remember, in England, the first time he ever saw an aurora, he was very old. He was like 50 years old. And that was because he was born at the time when there were very, very few sunspots. The children that I've given birth to worry quite a bit about my acne. The third is especially concerned, and 154 years ago I gave it a real fright when actually something happened, and we'll go to that in a minute. And these doctors say, I will keep having spots as long as the pesky magnetic fields don't start at monopoles, and providing I keep spinning. There's a clue there. Magnetic fields survive in fluids because we don't have monopoles. electric fields don't. And secondly, the spin is breaking symmetries, differential rotation, in a way that allows us to get large-scale dynamo action of the kind that Fausto was mentioning earlier. But what do us doctors know? Maybe we're all wrong and we've got the wrong theories, but I will present what we think we have. Why do we care about this stuff? After all, sunspots are benign things, right? This is really boring. I mean, this is this is taken from space, so you don't have to worry about clouds and nighttime or what have you. I mean, what gets more boring than a movie like that? That's like a day's worth of solar rotation. These don't do anything, of course. The really amazing thing is that, why would it choose to appear in these blotches and not sort of diffused all over the surface? I mean, why would it appear in those very concentrated forms? That question is still not answered. We don't know why it forms. The sun is obliged to form a sunspot. Sunspot, as we'll see, is something that is concentrated magnetic field. So there was a very famous observation, 1859, by a well-known observer of the time. The guy was watching and counting, drawing sunspots. I mean, what could be more boring than that, right? Watching, drawing. It's like sitting and counting stars. And maybe watching stars change their brightness a bit. Well, wait a minute. There was an experiment called Kepler in space which just did that for like 100,000 or thousands and thousands of stars. Incredibly boring. Well, I would argue that astronomy is the task of turning something that's, to most people, incredibly boring into something incredibly interesting and important. The more boring the work you do to the outside, the more interesting results you're likely to get, in my humble opinion. And I will show you some stuff now in which you can go, gee, look at that solar flare go off. Isn't that fantastic? Yeah, oh, NASA can make some money out of this. We can show it on CNN and see this solar flare, and perhaps we'll get some aurorae. That's all fine and well, but that's not science. There's no question being addressed there. Whereas if you sit and count stars and look at their variability, you can ask the questions like, I wonder if the sun changes in the same way as most stars do, and if not, why not? That's a more interesting scientific question. So the reason I bring that up is that it's frustrating being a solar physicist these days when people ask you to predict things like solar flares, predict the unpredictable. And I actually, if I had my way, I would form an institute for boring astrophysics in which you're not allowed to use videos, computers, a pencil and paper, and you put a bunch of people in a room, you don't let them out until they run out of some paper. And that's totally different from what most people do these days. I worry that a lot of the young people in astrophysics are being trained in technology, not being trained in science. So if you listen very carefully to the kind of thing Fausto is saying, he's exemplifies in my mind world-class theoretical physicist. It's the understanding. So what did he see? Well, nothing in particular. Here are some sunspots. He drew these little guys here that were really bright. Okay, and this was witnessed, reproducibility as part of science, this was witnessed by another person in 1859. And so this was a result that was at least confirmed by one other person completely independently. Curiously enough, in the next day, so these two guys saw this thing. It was immediately followed by a magnetic storm of unusual intensity. The auroral displays being most magnificent on both sides of the Atlantic and even in Australia. This was a major perturbation to the Earth's magnetospheric system as a result of something happening on the sun. Here are some traces, not very easy to see. This is taken from 1892. This is the measurements on the ground of magnets, altitude, and azimuth. So this storm, whatever it originated from in the sun, generated a perturbation that was very clearly visible. And already in Young's book, 1892, 121 years ago, one is talking about space weather. We think of space weather as being something very modern, but really no. It's way old. With modern space observations, so now we go from 100-odd years ago to just a mere decade ago, and you're familiar, many of you will be familiar with this stuff. What we're looking at is a close-up of an active region, so this is magnetic flux bubbling through the surface of the sun, emerging into this thin region called the corona, causing all kinds of explosive, sudden release of energy in the sun's atmosphere, including in fact the ejection of plasma from the sun. If you remember what Fausto was saying, if the plasma is glued to the magnetic fields, this means we've got to snip the plasma off. But this is not diffusive cutting. This is some kind of dynamical reconnection, which does involve diffusion, but is driven by something quite different. The sun's trying to deal with the fact that it's got magnetic flux emerging through its surface, and somehow this has got to go somewhere. How does it do it? Well, it gets snapped off and reconnects somewhere in the atmosphere, causing a flare. These things here are actually the result of that flare going off and particles coming from the sun, hitting the detector, which normally detects white light. But the detector is also sensitive, of course, because it's an electronic detector, solid-state detector, to the presence of ionized particles going through space. This is sitting outside the Earth's magnetosphere, this instrument, 1% of the way to the sun. And it's catching these particles, and they're showing up here. So this gives you a complete picture of the origin region of the sun all the way through to the detection of accelerated particles. These are very high-energy particles onto the detector out in space. So why does society care? Well, they want to know when these poor Canadians get their electricity cut off, 9 million of them, which is about, what, 20% of Canadians or something, had their electricity cut off for 9 hours. You know, you can say, oh, you know, so what, poor Canadians, you know. We had this terrible thing happening in Southeast Asia recently, which is a much, much bigger deal, and I think everybody agrees with that. But nevertheless, this does draw a lot of attention. You know, a lot of hyperbole, a lot of exaggerated statements come out about what might happen if the sun produces a Carrington event. The 1859 event is the biggest one on record. The one that caused this is significantly smaller. So there are fearmongers amongst the scientists that will jump upon getting funding by saying, hey, let me predict when a solar physics event is going to happen, and give me the money to do it, and you know, we will succeed in predicting solar flares for you, and et cetera, et cetera. I personally doubt the integrity of that kind of approach. I think it's analogous to, I was talking to one of you last night. What's going on here is magnetic energy is being stored very slowly and it's released suddenly. In the same way, thunderclouds build very slowly but release suddenly. Will you ask a weather person to predict if you will get hit by lightning on Teide Mountain on Wednesday at 2:30 p.m.? No, you wouldn't ask that person that question. They shouldn't ask the solar physicists to predict solar flares in that fashion either. They should couch it in different terms. And the solar physicists should be able to fight back and say, no, I think there's a 1% probability of it happening over a certain period, of which 10% of those may be headed towards the Earth direction. And I think that's a more responsible way of doing it. Okay. So a foul day in space weather can be replaced by this is the first words Macbeth utters in his play. So foul and fair a day I have not seen. I like to try and be Jean-Luc Picard of the Starship Enterprise sometimes. Well, I'm about the same height, not as good looking, and I have maybe the same amount of hair, so there's a great deal of beauty here. You know, the public is very interested in knowing origins in this, and we can't tell them often enough. And I'm sure many of you have interacted with the public to talk about these things. This is a direct result of particles streaming into the magnetosphere as a result of reconnection on the sun. some reconnection at the Earth, and the generation of electric fields locally, which can accelerate particles in both those situations. And they finally hit the more dense atmosphere and start to radiate. So this is a collision. What you're seeing here is light that came from the energy of the magnetic field in the internal energy of the sun originally, that's now coming directly from the impact of things like accelerated electrons, particles that may have been solar particles for 4 times 10 to the 9 years, but are now coming down the field lines on the fixed magnetic field of the sun, of the Earth, and are impacting things like oxygen and atoms and nitrogen molecules and what have you, and radiating at these wavelengths. If you're interested in Hollywood, one of the things you can do is make it. I mean, these sort of apocalyptic movies are very popular, and actually they've improved a lot since the days of Ernest Borgnine and other people in these old movies that are sort of hackneyed disaster movies. And while I haven't seen one yet, there may be an opportunity for someone to make a movie about solar flares because, and it's not because of anything we know about the sun, it's because of what we know about stars. And so what does this show us? This shows you the distribution of the number of events classified as flaring events in the sun. So these are with a certain amount of frequency as a function of the energy. And I don't want to go into the details here, but these are simply looking at the outer layers of the sun and looking at the radiation coming out from it and saying, well, we've seen some brightenings on a certain time scale. We count them up and we get a certain amount of frequency out of this thing. Here is the Carrington event. This is the strongest one that's ever been recorded in history on the sun, right here. I mentioned this boring spacecraft which just sat there. It didn't even take pictures of the stars in focus, for God's sake. They're out of focus deliberately. This photometry was the goal of this particular spacecraft. So here you have a defective spacecraft, like me with my glasses on. I can't hardly see anything now. It's out of focus, and all I can tell is how bright things are. And it sits and looks at the same part of the sky in Cygnus for 3 years and measures how bright things are. That's all it does. What could be more boring than that? Well, just look at this distribution here. These are old, slowly rotating stars. It's easy to find flares on rapidly rotating stars. I can put them in a close binary situation and have tidal interactions such that I have 2-day rotation period. The sun rotates once every 26.5 days. So what is important to do is to compare the sun to sun-like stars. So what they've done here is to select stars that rotate with periods of about 12 days or longer, and they've plotted up how often they find superflares, and they've put it on the same plot because now use the ergodic hypothesis, the sun in time, the stars statistically at one time. You can plot them together. And we find that, in this kind of situation, we're going to end up with something like 100 times the intensity of a Carrington event in principle can happen on the sun once every 800 years. As far as the biosphere is concerned, aside from the last, say, 50 years, where we're so heavily, or even 100 years, since electrification happened globally, we wouldn't give a damn. Yeah, a major perturbation in the ionosphere. Okay, so a few, Elizabethans would look up and go, ooh, look at this, isn't this great? But that's pretty much, and they wouldn't be able to use their magnets for going from Tenerife to South America, or Christopher Columbus might have had some trouble actually finding his directions based solely on a magnet. But But what I'm saying is that if one of these happens sometime in the next 800 years, I think there is a good chance that you may not even be able to drive your car. I mean, if we've got GPS built into the cars, if we've got safety mechanisms built into them, we have a major event in the Earth's atmosphere in which very large electrical changes in the magnetic flux are occurring in the ionosphere itself. They will induce electric currents on the ground everywhere and could potentially damage a lot of things. If our infrastructure is so much geared up towards that, then we could be in trouble. And this coming from a mission designed to find planets around other stars. It wasn't even designed to do this. Well, they knew they could do it when they designed the instrument. All you're doing is measuring the brightness, visible brightness and time of stars. So you're measuring the transits of planets, and you're measuring little bits of variability as a result of sunspots, star spots, and what have you. So, more importantly, why do we actually care? Well, if it weren't for the magnetic field and its variations, I don't think we would care. I would argue that essentially all solar physics of interest nowadays is concerned with understanding this as a function of R and T. That's what solar physics is. If you go out and ask somebody asks you what it is you do, I sometimes have a hard time because I do spectropolarimetry, I do some funny things with hydrodynamics, magnetohydrodynamics, simulating spectra and what have you. You know, it's very difficult to say. But if I say, I'm trying to understand how the magnetic field of the sun varies with time, why do you do that? Well, because it can do the things I just showed you. Then that's pretty easy to do. This, I think, in a nutshell, is what modern solar physics is about. It wasn't always like that, right? I mean, in the 1920s, we didn't have things like an equation of state for the balance between electrons, protons, and hydrogen until Saha came along and gave us that. So, you know, in the 20th century, we've come a very long way, but essentially all the classical physics has been worked out. Okay, so let's get into the physics. If the sun merely consisted of a nuclear core, a radiation zone, convection zone, and some stuff on the outside, we certainly would have local variations due to things like granulation. If I put the kettle on and boil the water, I get little pockets of stuff that's turning over that's smaller than the scale of the kettle. Not quite a fair analogy because you've got to change the state, you've got steam bubbling through, but nevertheless, if I put oil on and watch it convecting, then you know that we're going to get small scales and we're going to get some random variations as a result of that. But any really global variations we would expect to see of any serious magnitude of a star like this would be on the time scale of a Kelvin-Helmholtz time scale, which is simply the thermal energy contained in the star divided by its radiation loss. And that's on the order of 100,000 years. So we know that nuclear time scale is much longer than that, in the order of 10 to the 9, 10 to the 10 years. We would, however, expect if we bashed the thing to ring. And that typically, for the sun, has a period of 5 minutes. For giant stars, it's much slower. For smaller stars, it's much faster. So if we see things changing, as we know, the dynamo changes the sun in a period of 11 years. Something really strange is going on that's somehow not related to this. And, of course, that thing is the magnetic fields. What I'm showing here is a plot of the rotation rate as determined from helioseismology. One of the things you can do with the sun is observe the oscillations. The oscillations don't travel just on the surface. They're body oscillations of the whole thing, like a piece of jelly. And just like a jelly, if you knock it, you should be able to tell what the density structure of the interior of that jelly looks like by looking at the normal modes of oscillation. So the normal modes of oscillation of the sun, actually they're generated by very fast-moving fluid that's downflowing from the surface as a result of the escape of radiation. Remember, this is not a closed system. Nothing's in thermodynamic equilibrium here. We've got a core and a flux of energy going out. It's a steady state, but it's not thermodynamic equilibrium in any sense. So the outward-going radiation is accompanied by cooling of the plasma, leads to rapid downflows, generation of sound waves. Those sound waves rattle around, and the sound waves refract and do all kinds of things in the interior. And if the interior is going faster, as in this color, the sound waves are vectored along with that, Doppler shifted with it. We can see this. We can invert this problem of looking at the surface oscillations and get at the interior properties. So in the late 80s and early 90s, this was sorted out. What we see here is we have a zone where we can't find anything out in these things here. And modern observations with new spacecraft are starting to fill some of these things in. But here we can see that we have a very rapid rotation rate here, a lower one here, and there are sort of gradients which are in latitude and in radius here. So here are some shearing motions in the interior of the sun that we know about. As soon as these results are published, whole classes of models of dynamo could be dismissed because they were assuming reasonably at the time that there were very different looking profiles, such as rotation in cylinders, constant rotation in iso-rotation in cylinders. Those classes of dynamos don't work. So this is the kind of thing which we need to look at in order to find out how the sun's dynamo is working. And when I point out, solar magnetism, a physical perspective, this is basically what I mean. Why is it? What are the questions we really want the answer to? Why is the sun obliged to regenerate its global magnetic field every 22 years? Of all periods, why would it choose to do that? I mean, why not 111 years? Why not 10 to the 7 years? Why not 10 minutes? Well, we'll see what we've learned from that. Especially given these two timescales here. Why does it have to form a sunspot? What is a sunspot? It is a concentration of magnetic field where pretty much there's nothing else around it until it starts diffusing as the turbulence starts to break this thing up. Something in the interior of the sun wants to really generate something really strong inside there. The mean field models that Fausto was talking about derive equations for the mean magnetic field of the sun. The sunspot has a kilogauss, 10 to the 3 Gauss field strength. The average magnetic field on the sun is about 1 to 10 Gauss at any given time, averaged over the whole surface. What is the meaning of a model that generates 1 to 10 Gauss fields when you have to deal with things like 10 to 3 Gauss sunspots? That's a good question. So if you're using a diffusive model, a mean field model, to describe the evolution of the sun's magnetism, but you only look at the sunspots, there's another additional problem there. You have to explain why they're so concentrated. And that's a long-standing problem. Good news for you guys, any of you interested in solar physics, is we have, at least in the United States, the Advanced Technology Solar Telescope coming online in 2019. In Europe, they may get something called the European Solar Telescope, which may also have similar capabilities. Those are the kind of instruments which are starting to look at the diffusion processes in turbulence that Fausto was talking about, such that you replace this with an n of tau, and then you can start to understand the workings of the dynamo in terms of the genuine diffusion of magnetic fields, because right now we can't really do that. Why is it obliged to form a corona? We're so used to seeing the sun. Oh, it's just a bunch of sunspots. Yeah, eclipse happens. Oh, I see the corona. Woo! Isn't that great? Wonderful. I've never seen it, actually, even though I spent half my life working on it. Has anybody seen the corona eclipse? Nobody? Yeah? Hands up, guys. Yeah, I'm a loser. So I have never seen one. I would love to. Where did you see it? Colombia? Yeah? Yeah. We have one in 2017 in the U.S. going right across the middle of the U.S. if anybody feels like joining in the fray. Why is it supposed to produce a flare? What's that, you know, what is it according to the basic laws of physics? The equations of magnetohydrodynamics, for instance, that Fausto was telling us about. What's going on in the magnetohydrodynamics to cause this behavior? Because from first principles, I don't think anybody could have said, unless we'd observed it first, that we would have expected any of this. Right? That's the kind of problem that I would like to get to. Here is the grand challenge problem. Here is the sun's corona. As observed, we go from the surface of the sun, these boring sunspots, and then as we come up, we see these wonderful, beautiful loop-like things that appear to look like the field lines traced out of a bar magnet. Potential fields originating from currents underneath the surface, emerging out into the atmosphere, associated with the sunspots. Already 70 years ago, in the Second World War, Ed Lane published a paper, a Swedish spectroscopist. This guy spent his time with a spectrometer bashing ions into each other in a laboratory and observing the spectrum coming out of them. In the 19th and 20th century, they took spectra of the sun. People like Huggins, Janssen, other people went to these eclipses. It was great to go to these eclipse expeditions in India and all these wonderful places. And they found these lines that nobody could identify. This is the origin of helium, of course. Helium is named after the sun, of course. It was discovered first on the sun and only later on the Earth. The lines that Ed Lane discovered, and you can be damn sure. I mean, the Swedes are a fairly conservative nation as a whole. Ed Lane I met him once, and he's a very nice conservative chap. You can be damn sure he was not going to go out and say, look, I've found that this must belong to an iron atom with 10 of its electrons stripped off it. I mean, that's like 1,000 electron volts. That's, let's see, 1,000 times 11,000 Kelvin. That's 11 million kelvins worth of energy that I would have to use to make that ion appear in the sun. Well, we've only got 6,000 degrees at the surface. How in heaven's name could I produce something that's at 10 million degrees out here? It's a mystery as to why the sun is obliged to do this. We know for sure by looking at stars that every other star with a convection zone and a little bit of rotation, every star that we know about rotates, does exactly the same thing at various levels. This is a universal phenomenon. Something about the magnetohydrodynamics and the plasma physics is dictating to us that this is a very general result. Quite clearly, it violates the second law of thermodynamics. You can't get heat from cold places to warm places, so there must be a non-heat kind of transport. It's not a thermal process. It's a non-thermal mechanical kind of process. Okay, let's speed up a bit. This is the gee whiz stuff I'm talking about. These are beautiful pictures which you can easily go and find on the web. One thing I would like to recommend to you is the physics of solar flares. Most NASA and other symposia, okay, you can find some nice things these days. This is an absolute classic, 1964. You've got papers by Petschek. Anybody heard of Petschek? He's the fast reconnection guy. Papers by Thomas Gold. Thomas Gold was a wonderful guy that was in charge of science on the Apollo missions, for instance. Very controversial figure. He claimed that all the oil in the interior of the Earth was nothing to do with the biosphere. It was just naturally there as a result of organic compounds formed in the interstellar medium, I suppose, or something. Gene Parker. This is one of the best collections of paper. Carmichael has a paper in there on flares. These are classical papers on hydrodynamics, magnetohydrodynamics, and a beautiful statement of the flare problem in terms of basic physics. Solar magnetism in history. Already in 1870, and one of my classes we were talking about this kind of thing here. There were spectral signatures. This again is 1870. Now, the Zeeman effect wasn't discovered until 1896. But here is the Zeeman effect present in the spectrum of the sun, which it must be. You take a spectrum, you draw it. They didn't photograph this one. It was a sketch. But here it is. Here is a sunspot, and here is the splitting due to the Zeeman effect. The problem at this point was nobody knew that there was a spectral signature of a magnetism. Nobody actually took a Bunsen burner and put a magnet next to it and observed the spectrum. That's what Zeeman did. Okay? So this was interpreted as some kind of phenomenon that they'd seen in other lines, namely the chromosphere. These are called non-LTE effects, which I don't want to go into. But there was some kind of understanding of this in another interpretation. Okay. Remarkably, 1852, the sunspot cycle discovered by Schwabe, who was a Germanic chemist. He sold medicine in his shop. He was interested in the spots on the sun. I mean, again, incredibly boring science. This poor guy is sitting there and counting the sunspots, and he noted there's a pattern. And Wolf reconstructed these, having seen them over many years. But here is a record going back to the 1780 of geomagnetic activity. This is just magnets moving around. And the RMS motion of these magnets away from what the steady Earth's field is doing is documented in these things. So they already knew about this stuff implicitly, even though they didn't really know that the sun had a magnetic field even at this point. Another hint was that the sun just looked like a magnet to people when you saw it in eclipse. This is a plate from 1878 that was scanned in and digitized. These plates were only sensitive to blue light. That didn't happen until 1908. But nevertheless, what one sees when one does an edge detection, you can see kind of the idea that one's got rays that kind of look like a bar magnet coming out of these things. If you do some clever things by combining images, you can take the old plates and turn them into what look like modern photographs of the corona. The data people acquired 110 years ago, while the detectors were not electronic, etc., were beautiful. If you treat them in the way that they deserve treating, and actually try to recover from those plates what the information they contain is. So I have an enormous respect for people that can go to an eclipse, take a bunch of plates out in the desert somewhere, and get images that can be reconstructed like this. And these kind of things are incredibly useful because if you think about it, since then, the sun has gone through how many cycles? Well, it's 1901 to 110 years divided by 22. It's only 5 cycles. That's not a lot of cycles. So these are important to study, the history of this stuff. Okay. 20th century. Jose Carlos del Toro Iniesta, notice the institute here, wrote a beautiful historical survey of what was going on around this time in the discovery of the Zeeman effect. And of course, in astronomy, with the exception of 1 or 2 neutrinos and with the exception of cosmic rays, we're stuck with photons. There's not a lot we can do about astronomy at all because it's all remote sensing. The same is true of the sun. Solar probe, which some of you might have heard about, you think to yourself, well, it's going to fly into the sun. No, it goes to about, does anybody know how close this probe spacecraft is going to go? Is it like 10 solar radii? Yeah. 9 solar radii, basically they missed the sun. right? I mean, that's very, very far out. And there's reasons for that. Our technology cannot survive much closer than that. So we're really in the business of remote sensing. And what Jose Carlos is documenting here is really the beginning of solar physics, I believe. I tell you what, why don't I stop here and continue? This is not the complete first lecture, but it's 1:25, and I was guilty of not signing the sheet outside because there were other people signing it. So, is that okay? Should we continue? I think I should stop here, otherwise. Okay. All right. Thank you.